Hello, Internet. We are live.
Hey everyone, welcome to episode 31 of the Stanford MLSys seminar series. I'm Kran. We have with us Dan, Fyodor, and our guest today, Pete Warden. Piero could not be here because of he's a little under the weather this week. So we hope you're feeling better, Piero, and come back next week. So as always, we're going to have a 30-minute podcast style discussion. Sorry, a 30-minute talk followed by a 30-minute podcast style discussion where you in the live audience can ask questions. Today, we're going to be talking to Pete about TinyML. So a little bit about Pete. He is the technical lead of TensorFlow Lite Micro, which is Google's open source embedded ML framework. He was previously CTO of Jetpack, which was acquired in 2014, and he has authored a book on TinyML. He's quite well known. I like to think of him as the TinyML person because all the TinyML talks that I've seen have come from him. But yeah, Pete, take it away. And a reminder to the audience that if you want to ask questions, feel free to post them and we'll keep track of them during the talk, but we'll get them across to Pete at the end of the talk. So yeah, Pete, take it away.
No, thanks so much. And yeah, just to reiterate, I'd love to have a bunch of questions coming in. So please do, please do post them. So yeah, thanks for having me. This is a fantastic series. I saw that you actually had Song Han, who's a former colleague whose work I still follow pretty closely on previously. So you've already been looking at the whole TinyML world. So I'm excited to be able to talk about machine learning everywhere and kind of some of the big picture, hopefully, of TinyML and what we're doing with TensorFlow Lite Micro. So if you want to follow along at home, you can find these slides I actually made public at tinyurl.com/S46J7ARW. And maybe one of the hosts can add that to the description, if you're looking at this afterwards. And the way that I'm structuring this is trying to use the paper that we did at MLSys this year about TensorFlow Lite Micro, our open source framework. I'm trying to have this talk kind of be a companion piece to that paper. I'm not going to be going through the paper itself in detail because you can read it yourself, and also there's a great talk by my colleague VJ up at Vimeo, which you can find at the link below, which goes into some of the background and really tries to kind of explain some of what we're doing in the paper. And really what I want to do is focus much more on some of the things that kind of didn't make it into the paper, some of the motivations around why we're doing the paper, why we're doing this technology. And coming from my background as the technical lead on this TensorFlow Lite Micro open source project that we're doing at Google. And as I said at the start, here's my email address as well for any sort of follow-up questions that we don't get to cover in this podcast. And I'm pretty active on Twitter too, if you just want to casually ping me there. So if you're wondering what TensorFlow Lite Micro is, the key difference between it and some of the machine learning frameworks that you may be more familiar with is that it's designed to help you run models on devices that are really, really small, that may only have tens of kilobytes of memory. And this is something that I've found fascinating ever since I joined Google back in 2014. One of the first teams I talked to was the team that actually does speech recognition on phones. And I'm going to have to be careful about how I say this phrase because I don't want everyone's phone to go off. So I'm going to pause in the middle. But okay, Google, or as we call it to avoid all our phones going off internally, OKG, actually was using a neural network model that was only 13 kilobytes in size. And when I joined Google and discovered that, that kind of blew my mind. The fact that you can actually not only use an ML model that small, but it's actually the best solution, back in, 2012, 2013, 2014, when they were doing this, even back then, kind of when the deep learning kind of revolution was still in its very early stages, that was actually the best solution, even compared to all of these sort of, more traditional machine learning approaches and other approaches that they'd looked at. So that was really the seed for me over the years. I really wanted to work in this area because I was just so curious about the fact that you can do really cool stuff in just tens of kilobytes of memory. So we've got this MLSys paper that I talked about, and it describes the system that we ended up building to deploy these models on these really, really small systems. And as I mentioned, we've got that Vimeo video of the MLSys talk where you can get more information about the paper itself. I'm not going to focus on the minutiae of what's in the paper itself, but I do want to talk about the bigger picture. Why is this area so important? And what are the kind of things that didn't really make it into the paper, or the unexpected challenges that we encountered while doing this? And really, why is TinyML so important? Or why do I think that it's such a crucial thing to be working on? And for me, it's really the applications. The things that we're going to be able to use this stuff for are what make me so excited to be working on this. And I recently came across this framing, this way of thinking about it, which really tied in with the way that I'm seeing things working, where you've got this first era of computing, through the 50s, 60s, and 70s, where you had to go to a mainframe if you wanted to do any computing. You actually had to kind of have a terminal that was physically connected to one of these, $1 million computers. And so if you wanted to do anything, you went to the machine. We've advanced beyond that in the personal computing era. First off, we started to have computers that could be in our home, and eventually we progressed to like laptops, and then phones that we can actually carry around with us, even sort of things like wearables. So that was a massive change in how we relate to these computers. But what I really see happening with TinyML is this new idea of ambient computing, where you aren't taking care of computers that you sort of carry around with you. The computers are already there. They're all around us in our environment before we get there. And they're doing their job kind of without us around and without needing any care and attention from us. And you might be wondering, what has that got to do with machine learning? This sounds like a cool vision, but why is machine learning so important if we are going to go in this direction? So to understand that, we have to talk a little bit about these use cases. The sort of things we're looking at. We've seen some amazing things happening with environmental and ecosystem monitoring. So things like, if you look up Plant Village, they're an awesome nonprofit out of the University of Pennsylvania, Penn State, I should get that right. And they're actually doing plant disease recognition using image algorithms and ML models to actually help farmers in developing countries take photos of their plant leaves, and locally on the phone, since they're unlikely to have good data connections, actually do the diagnosis of plant diseases. And if you think about being able to extend that, so you just have sensors that are cheap and everywhere that can actually detect plant diseases and pests, and help reduce the use of pesticides, help make sure that endangered birds and animals are actually looked after. You can start to imagine how having sensors that are scattered widely can be really, really useful. One of the things that I don't miss from being in the office when I was at Google was in conference rooms, we have motion detectors tied to the lights, which is really good news for trying to save energy. But it meant that if you were in a really boring meeting and you didn't move enough, the lights would go off, and so you'd have to kind of stand up and do some aerobics in order to get the lights to come on. I'm really hoping we can get into an era where our built environments, and our things like cars and public transport are actually able to tell when people are around to kind of tailor the AC, alter the lighting, really save a lot of wasteful energy usage, but also be a much more welcoming and smart places for us to be as people. And one thing that I am absolutely convinced is going to be happening, which from the technology side is like so close, is being able to have little 50-cent chips that can run on a very, very small amount of power, that can have full voice interfaces. And I think once you have those, anywhere that you've got a switch or a button or a slider, any item, whether it's a TV or a toaster or a light or a fan, should be able to respond to a voice interface, respond to voice commands. And one of the questions that comes up is like, well, how are you going to do that if you have to have like wake words, like like the one I mentioned earlier? Well, I'm really interested in using gaze detection, having tiny low power cameras where you can look at an item and it will know that you're talking to it, because that feels like a very natural interface. And all of this, we have the models, the ML models for doing this kind of voice interface. I'm going to talk about the hardware that's required to do this. We have the ML models for doing gaze detection. It really just feels like a kind of an engineering and organizational challenge before we can get to this point where we have this kind of little component that you can just buy off the shelf that lets you build a voice interface into any system. So I'm really excited about, trying to just join the dots and see if we can help make that happen. So what is the biggest obstacle to this? All of these applications I'm really keen on seeing out there in the world. The biggest problem that we face is power, energy. As I mentioned, in the personal computing era, as I've defined it, we have devices that, oh, I'm sorry, an auto updater just kicked in, so this is the bane of my existence. Okay, let's and there we go. So the personal computing era that I mentioned, it relies on us either having devices that are plugged into the mains, or it relies on us charging items or changing batteries. And I mean, that's kind of okay for when I've got one phone. You know, I can just plug it in the nightstand every night, and that's not too much of a burden. But if you imagine having, you know, 20 or 30 or 40 or 100 devices that you want to have in your environment kind of ready there waiting for you, the idea of either charging them or going around and changing batteries frequently for those, it just doesn't scale. Like, nobody's going to you know, put up with that kind of environment. So we're forced to rely on having devices in these environments that either have batteries that are going to last for a long time, so we don't have to keep running around and changing them, or on something that's using energy harvesting, some kind of solar power, sort of, you know, thermal differential, all sorts of other kind of, you know, even harvesting like radio waves. There's all sorts of really interesting ways of kind of getting small amounts of power without having to have batteries. So if you think about a reasonable target of saying, hey, I'd like my device to run off a pair of AA batteries for a year, if you work out the energy budget, you know, it's in the, you know, sort of ballpark of sort of 1 milliwatt of kind of continuous power. And that's kind of in the similar sort of range to what you can get from, you know, smallish indoor solar, you know, not in direct sunlight, sitting in a room, maybe powered by, you know, lighting. It all works out to be somewhere around that same sort of range. And the big problem is that radio technologies, even things like Bluetooth Low Energy, which are designed to be really, really efficient, they're using at least tens or, you know, somewhere around 100 milliwatts when they're active. And that's for just a very short range technology. And longer range, you know, using like cell data, LoRaWAN, or these other kind of things that can go more than a few meters, it takes even more power. And the reduction in the amount of power that's required does not seem to be improving, you know, in a very, you know, fast manner. You know, it's going down, but it's, you know, feels like it's on the order of like a few percent, you know, a low single digits percent a year, which means that this isn't likely to change in the next decade or two, you know, dramatically by, you know, an order of magnitude. And this means that the current model that we have of things being always connected to the internet, you know, that's what makes my phone great, what makes it possible for me to be doing this talk from my laptop. That makes deploying those deploying that systems approach really impossible. And that's where local intelligence is going to be so important. So you can actually capture microphones, accelerometers, video, sort of images with very small amounts of power required. And you can also do a massive amount of arithmetic on a chip in extremely small amounts of power. You can do, I'm going to talk about sort of tens of millions, hundreds of millions of arithmetic ops a second and still stay well within that 1 milliwatt budget. So that means we can fit both capturing data and running an ML model within that sort of 1 milliwatt budget that I proposed. And then only wake up the radio when something important has happened that you kind of want there to be some action taken on, like, oh, somebody entered the conference room, a crop pest was spotted, or, oh, there's, I haven't talked about medical devices, but, having something that's like, oh, there's a reading here that indicates that there might be some kind of, potential medical issue. Then you can duty cycle the radio. So you still have that connectivity, but only when you actually need it. You're not just sending kind of, dumping raw data over the connection all the time. You might only wake up like once a day or once a week when something that matters might have happened. And to make this happen, the good news is that the hardware is already there, and the hardware manufacturers are really excited about this ML stuff because they can finally sell arithmetic. There wasn't much reason to do loads and loads of arithmetic on, these devices before, but it turns out it's pretty straightforward for hardware designers to offer arithmetic pretty cheaply. And, this example here of a device that, is in the 1 milliwatt power budget, it's about $3 per unit. But what I find really exciting is that the whole field keeps getting cheaper and cheaper. And it still blows my mind that you can actually buy a very simple microcontroller for just 3 cents. That's less than, I can probably buy like a resistor or capacitor for, and you can get this entire little, useful programmable thing. And I'm really expecting the prices for these to all keep dropping. And we've got the models for doing all sorts of useful stuff with image data, with audio data, with accelerometer data. They're out there. A lot of them are open source. So what we're left with is this systems problem. How do we take these technologies and kind of integrate them together into a very small area of memory with no operating system often too? And that's where these embedded ML frameworks come in. And TensorFlow Lite Micro is the one that I work on. So it's obviously very dear to my heart. But there's fantastic work happening through the sort of the TVM team. The PyTorch people have, Glow that has been very successfully used to generate code for microcontrollers. Even though it wasn't originally designed for that, but it's proved to be very useful. And there's I mentioned Songhan before. MCUNet is another great framework, and there's a lot of really interesting work happening out there. And what I find really exciting from a technical and kind of a research side is it's a really fun sandbox for all sorts of things. You're trying to fit everything you're doing inside these very, very tight resource constraints, which means that you get to try out all sorts of really interesting techniques. It's a fantastic testing ground for new hardware ideas, especially because we're trying to do massive amounts of arithmetic, And that means that using things like FPGAs to accelerate on a kind of a, hardware side, and build, prototyping new kinds of hardware can be really interesting. And there's actually a Google project called CFU Playground, which is billed as letting you build your own ML accelerator, which I think is a fantastic example of some of the things you can do with this. And for general ML ideas as well, if you're able to get kind of the iteration cycle and like the end-to-end round trip, so quickly, you don't need, hundreds of GPUs to train and test a lot of these things. It's a great way to just go ahead and kind of try innovative ML ideas without needing a massive budget. And some of the areas that I did find, most challenging and I wanted to highlight from our MLSys paper were the way that converting from a training environment over to an inference model can be really, really hard, because the damn researchers keep coming up with better ways to build ML models, which means new ops, which means anything that's converting from the training environment over to another environment has to kind of try and keep up with everything that's happening in the research world. And it's a super challenging environment to get stuff running in, because in the mainstream computing world, we pretty much only have ARM and x86 instruction sets. In the embedded world, there are literally dozens of different instruction sets running on incredibly different types of hardware that really will push your kind of engineering skills to the limits if you're trying to support them. So we had to really try and come up with some ways to deal with this massive variation and have something that was radically portable. And a question that always comes up is, why are you using an interpreter for your models? Why aren't you using code generation? And for the answer to that, I'll just refer you to our MLSys paper, because I spent some time on that. And, I do think that there's, we have found that there's been some important reasons for that. So what's coming up in the future? What's really cool is that this is a very, very young field. There's a lot of problems still out there. And I know that what we've done with TensorFlow Lite Micro is a long way from the final word. There's plenty of room for all sorts of different approaches. And I'm really looking forward to people coming up with their own, angles on all of these problems. And I'm really looking forward to learning from all of these. And it's also really important because, like I mentioned earlier, I think that this is going to be a whole new area of computing. There's going to be a whole new world that we're going to be living in, where computers are all around us. We've got this ambient computing idea. So the impact of what we're doing in this area can be, really high. Like the leverage that we have can be, super powerful. So that's another reason to sort of, I'd encourage you to look at this and, look at diving in and picking up a whole bunch of the research problems that are just lying around waiting to be worked on. So that's pretty much it for my formal presentation. As I mentioned, I'm always happy to, get offline questions too. For some of the background of TensorFlow Lite Micro, if you go to tinymlbook.com, you can actually find an O'Reilly book that I wrote together with my co-author Dan, who's over at Edge Impulse, which is a great startup working in this area, by the way. And we also launched some ways of doing cool things like magic wands with this Arduino device, and some drumming and all sorts of other ways of using Bluetooth to actually interface a microcontroller with a website at this experimentswithgoogle.com link that you can follow. So that's another great way to get started. And I think that's it for me. Hopefully we've got some questions from the audience, and I'll get kicked off screen share.
Awesome. Thank you so much, Pete, for the talk. And yeah, I guess for folks in the audience, just a reminder to send in your questions and we'll get them across to Pete. So to kick us off, I guess, I was curious about, like you talked a lot about embedded ML, obviously, and one thing I was curious about was like, I think I didn't hear you mention the word like, Internet of Things, or this, general concept. Right. And so I'm curious what your take is on that whole, whole trend, which I think was pretty big a few years ago, and then kind of, I'm not sure it died out, but it seems to be dormant.
Well, I have to be careful because it's such a vague term that it's now become like to mean anything embedded. But that slide I had about the radio, where if the Internet of Things, the internet, the whole point is that it's always connected. And if you want to be always connected, you're paying 100 milliwatts in power at least. Right. So that, unless you've got like a car battery attached to every little device, like just the physics of that don't work out. So that's really why I try not to attack it too much, even though I'm sort of, but it feels like the whole sort of concept behind that of having, it'd be great if we could do that, but the physics don't let us. So, this is an alternative of what we can do.
Right. So you're not very bullish on the future of the Internet of Things, I take it then?
I mean, who knows? Because the definition keeps changing, but the way I think about it from a technical point of view, these things are not going to be always connected unless there's some massive breakthrough in radio technology.
So actually on that note, so I was really interested in that you brought up kind of power as a like key bottleneck, and it wasn't one that I had thought of before. I was curious, do you think that there's any kind of like lower bound or any kind? I know like we in computer science, we love having concepts about like information theoretic bounds or hard bounds, bandwidth. The classic bound is, speed of light. Do you think there are like similar bounds for the amount of energy that you need to do some sort of intelligent task, maybe informed by nature or anything like that?
So my intuitive feel is that I don't know what the lower bound is, but that we're a long way from it, just because we've never had a arithmetic intensive, an arithmetic kind of bound workload like ML. Right. ML is like, we're going to do like millions and millions of multiply adds using, maybe tens of thousands of coefficients. So the ratio of memory access to arithmetic is radically different than, almost any other task that we've had. So that's what's made all the hardware designers so excited. Right. They're like, we know how to do arithmetic. We can do tons and tons and tons of it. We've just always been like, memory bound. So we've never had. So it really feels like they're just like having loads of fun at the moment, just kind of like beefing up their arithmetic units, and not having to make the memory, not having to worry about the memory bandwidth. So right. It definitely feels like there's orders of magnitude still to kind of go downwards. We're at like picojoules that we're around like single digit picojoule per multiply add. At the moment, is kind of, the best practical numbers that we're seeing. And so I feel like we can keep kind of pushing that number down. It feels like almost like a Moore's law type situation for the next, hopefully decade or so.
Right.
So
yeah, sounds really cool.
Let me ask kind of a slightly different question, because if I'm, for example, building an application, I'm wondering if I need to send the data collected by my sensors to some like centralized node that's plugged into the wall, or should it be computed, remotely on device at the edge? What's like the bit rate at which like I know I can no longer like send this information, that there's too much power spent on Bluetooth or whatever it is, and I have to start relying on onboard compute?
So the hard part is that even to just send one bit, you need the radio turned on. And just having the radio turned on, you're instantly paying that sort of, whatever it is, 100 milliwatts, or, we can argue about the exact numbers there. So you've got this kind of like floor where to go from 0 to 1 bit is, you have to turn the radio on, and usually the radio has to stay on. Bluetooth Low Energy is much better about this, but in a lot of cases, like with Wi-Fi and cell and things, the radio's on for like 13 seconds or something. Even if you only send one like byte across the network, it kind of has to spin a bunch of stuff up and then spin it all down.
So basically, it could be a problem even with 1 byte a second or something like that, because it basically has to always be on as a result.
Yeah, and what you usually end up doing is like, okay, I'm going to batch that. So I'll send like 60 bytes every minute, but then you've got like a minute's latency on any reaction to stuff.
Yeah.
So it's this very frustrating situation. It's always been this hope, and I don't understand the hardware well enough to understand kind of why we haven't been able to solve this from a radio side, but I've been kind of like poking at it and like asking people who do know for long enough to sort of feel like there's this fundamental problem of sending bits any physical distance without burning a bunch of power. So
that's so interesting.
Pete, I wonder, how do you guys kind of in the TinyML community, are you viewing things like the recent trends, I think, in the general ML community to like bigger and giant models, like, last year GPT-3 and models like that? How do you kind of view that kind of like development and those trends in the context of your vision for like, tiny models that can fit on kilobytes?
No, I mean, it's been really interesting. I mean, I almost see them as, they're a great source of training data, because if I can use a really good model and use it to label a bunch of data and train a really small model, or use like a teacher, student, approach, that's great. And also, I feel like a lot of those really massive models have been around text and translation, and that is really a realm where we haven't seen applications really for that in the TinyML world, because the closest we come to that is like voice recognition, and still there, Google's got server quality voice recognition on the Pixel. We published that a blog post about how we fit that in 80 megabytes. So that's doing, kind of as good voice recognition as we've got, and we're able to run it locally on an edge device, not on an embedded device yet, because 80 megs is still a bit too big. But it feels like with all of the image and audio and speech recognition and things like that, we aren't seeing that, the returns from having these massive models in the same way that we are for language. But yeah, it's a really interesting point.
Yeah, that's really interesting. for me, it kind of begs the question of, do you think we'll ever have embedded devices that, could be as intelligent as, like, talking to some, I'm going to talk to the chip in my fingernail. It's going to like talk back at me.
I mean, one way I think about it is I would love to get a device that was as intelligent as a dog or a cat. Which is like, maybe it will sometimes follow simple commands if you're lucky. And then, for anything that's kind of more on the sort of human level, general AI sort of thing, I do feel like that is going to be like the GPT-3 sort of, right, server side, some crazy, data center thing.
We actually just got a question from the audience from Matthew Coe. And he's wondering, could non-neural approaches help with TinyML? What's kind of your experience been there?
Yeah, so there's some really good work out there. If you look at SensiML is a really good framework for doing kind of TinyML with traditional, more traditional machine learning approaches. If you look, Microsoft actually have their embedded, I think it's the embedded machine learning toolkit, which has, my rule of thumb is, if you've got data that's in any way structured, like if you've got like temperatures, or you've got like kind of like spreadsheet style data, then probably random forest is 90% of the time you'll just throw random forest at it and it will produce like, the right answer, or like linear regression or whatever it is. And where deep learning kind of becomes more interesting is for these really messy, chaotic data sources, things like audio, accelerometers, images, where you've just got this soup of things that you're trying to, massive soup of kind of things that you're trying to find patterns in. So yeah, I mean, I encourage people to use traditional ML wherever it works. Like, it's where it works, it's going to be way easier. But that's kind of my rule of thumb, is like structured data, traditional ML, unstructured data, you'll probably end up looking at something deep learning-ish.
So I guess I had a question which was maybe, going off on a different tangent, but I was curious how you think about, the experience that developers have when building embedded ML applications, because I think as I'm thinking through, like trying to build, let's say, an embedded ML system for some application that I might have, I guess one of the things that seems challenging is you have to think about a lot of different domain areas. Like, you have to know a little bit about hardware, software, machine learning, and then not just machine learning, you have to think about how to compress the model down to the right size. You have to think about all the power usage. You have to, deploy the system, maintain it. So I'm wondering, like, what are some of the, best practices there, and what are some of the things that you're doing as part of your own work in kind of addressing those?
That is very, very fair. I mean, I sometimes think of it, to use a much maligned kind of phrase, as a full stack kind of. You really, if you're going to successfully build an application, you really do need that. Hey, I understand how to train in a Python environment and on the cloud, and using GPUs, and then I understand how to like convert it down and do quantization, and then I understand how to like program an embedded device and use an embedded IDE, and it's a massive amount to try and like cram into your head at once. What I try and do is have very step-by-step recipes. So one of the nice things about the embedded ML space is that there really are only a few main kinds of sensor data that you care about. It's often like, hey, I want to tell if there's something in an image, or there's a sound, whether it's a speech or something else that I want to tell when it's happened, or I'm trying to recognize kind of some particular patterns in an accelerometer. And so what I've tried to do is put together like Colab notebooks and Python notebooks that walk you through all of the steps that you don't know, and then hopefully give you the chance to say, well, I'm going to leave everything else untouched, but this person detector is going to become like a dog detector instead. So I'm just going to retrain it with dogs instead of people, but everything else I'm just, should just work. Because it gets really, really hard once you sort of step off the well-lit paths. And it's not something that TensorFlow Lite Micro has been able to solve, or anybody else I've seen for that matter. So
and maybe out of curiosity, could you speak to some of the applications or some of the domain areas where you've seen kind of the most uptick in this space? So I think you mentioned like agriculture, like broadly being kind of a place where folks are trying to use TinyML to detect let's say maybe pests or some sort of degradation happening to their foliage in some way. So are there other kind of areas, or even in this area where there's been a lot of success and you're very hopeful?
So it's still pretty early days for a lot of these applications. What I've enjoyed following is there's actually a community called wildlabs.net. And they are a bunch of sort of like wildlife monitoring kind of nonprofit people largely. And they have a whole bunch of really creative use cases. Like one that I got covered in the New York Times a few months ago was actually doing facial recognition for bears. So they were actually able to kind of monitor bear populations, I think, up on like Kodiak Island or something by and that was not, that was still, they were still transmitting stuff up to the cloud and things like that, so it wasn't quite the pure, but there's a lot of innovation happening in that nonprofit world. And honestly, it also feels a bit like that, what I've heard of the sort of the early 80s and the homebrew computer club, where there were loads and loads of nerds out there who can see really cool things to do with this. We don't quite know what the real application is. I was around enough in the 80s as a little kid to remember that everyone was just building like things on their 8-bit computers to hold their like grandma's recipe collection, because or address books or something, because like we had no idea of what the it's like these PCs were nice things to have, but nobody really knew what the use was going to be. And it feels a lot like that now, that where there's all of these kind of things happening in the undergrowth that aren't part of the mainstream, where hackers are going off and kind of creating, especially at like nonprofits, like I said, like wildlabs.net and things like that. And some of them are going to catch on fire eventually, but who knows?
Yeah, it seems like a place where hobbyists would really enjoy it. I can tell it's a sort of tinkerer's paradise in some sense.
Yes.
Hey Pete, we had a question in the audience about training, and this was actually something that I was thinking about a little bit. What do you think the role of kind of like retraining or like retraining these systems is kind of in the TinyML world? I know that so I know that for my voice activated phrase that I'm not going to say out loud, like it has you like say it a few times when you like first get your phone to kind of learn your voice. What do you think the role is there? Like, is this something that will ever happen on a few kilobytes? Is that maybe the role of like cloud computing in the TinyML era?
Yeah, and exactly. I mean, that's already happening for OKG. That's a great example. And that is using not doing full retraining, but a lot of what I've been working on in that area is around using embeddings. So if you have an embedding and you sort of have somebody say the word 3 times, and then you look at that sort of, that little cluster of like 3 things in vector space, and then you like kind of draw a circle around that, and you say, okay, anything within this like cluster we're going to take as a true a true hit. Then that's a really nice way of kind of not having to do backprop,
Right.
which is a pain, because you have to modify and store. Anyway, it's you wouldn't want to do that, but you can do it as kind of this post process. And I sometimes think about that as like personalization of models, or kind of a very limited way of training. And I've actually been working with my colleague Vijay over at Harvard, who's been doing a lot of the, who gave the talk about the MLSys TensorFlow Lite Micro thing that's up on Vimeo. I've been working with some of his students, and we've got a paper, Interspeech, that's been accepted, talking about some of what we've been trying to do with these embeddings, and like this kind of like half pseudo retraining.
Right.
So yeah, that's a great point. I think that I'm hoping to see a lot of that sort of stuff, and I'm also hoping it may address the question about, hey, how can you actually do this without having this entire, if we can provide recipes where somebody can take a pre-trained model and then just supply a few examples of somebody saying a different word, and it will learn that word without you having to go through the full rigmarole. Like that's going to be a much better experience for people than what we currently have.
Yeah. That vision of like all training is just inference sounds really cool, really tempting. Maybe I don't have to use all my GPUs anymore.
Yes. I wouldn't short Nvidia's stock price yet, though. I think
It's a fair point.
Pete, I had kind of a comment I was hoping to get your opinion on. So one of the reasons I've heard for why these like tiny sensor driven systems haven't really taken off is because even though they've been around for like almost a decade now, at least, depending on how you define it, it's the ubiquity of smartphones, right? We're always carrying around essentially a power brick with a bunch of processors and a ton of sensors. And a lot of user-centric applications can already be supported by this like mobile device. So I was wondering, like, kind of, what are your thoughts on that? I know that the vision for ambient kind of computing is rather different from this, but what do you think?
No, I think that's totally fair. It's like the phones have been amazing in terms of just like eating up every other device that you have in your life. It's like that photo of like, hey, this is what we had in the 80s on a desk versus, and this is your phone. So I really, even that's why I'm not even really talking about things like wearables, because, they have largely just become these kind of parts of your smartphone, effectively, whether it's like, things in your ear or, on your wrist. So yeah, I think anything that fits into that model of you're kind of carrying it around with you, it's going to be very hard to resist that kind of gravitational pull of the phone. And I guess the only thing I would say is that what's been interesting is that the phones themselves have increasingly been switching off the main application processor. And like, when you're playing music or doing some other, stuff with the lock screen on, you're actually, the phone is running on these little embedded DSPs versus to sort of like save battery life versus actually running a traditional kind of,
So it turns into a lightweight version of itself when needed. That's kind of cool.
Yeah, because everyone's kind of facing this battery problem, and everyone's turning to like embedded devices as like kind of the solution. So I'm kind of hedging my bets there, even.
So we might have all these embedded devices on top of a brick, like in a single package.
Yeah, I hope not, but
I want to ask maybe a question that you probably get a lot, but is worth asking, which is, what your thoughts are on privacy and kind of, I think one of the things that is obviously kind of important with the ambient computing is the fact that, if it's a visual sensor and there are humans walking around, a lot of folks don't want their picture taken or to be part of that. So what are your thoughts on kind of, where that, is that a bottleneck for, some applications? Is that something that's been an issue?
Yeah, and I actually just shared a link to a paper that's kind of under review that I actually did together with Zane and Sachin and some, Kartik and Brian at Stanford, because one of the reasons, another reason I'm really excited about working in this area is you can stop the data leaving the device. You've essentially got this set of air-gapped, devices out there. And that paper that I shared actually talks about how we can make some guarantees about how recorded data just never leaves the device that it's on. Like, you actually can have some like secure enclaves and auditability of being able to say, no, you can't actually hack into this device to access the image sensor, even though there's an image sensor on there. You can't use it to kind of spy on somebody. All you can get out is, hey, there was a person in this room, or there wasn't a person in this room. And there's some, hardware level guarantees that that's all you'll ever be able to find out from that device. And just generally, I like the model of not sending raw data up to the cloud. Helps save power, but it also means that we have a lot more opportunities to have things that we can physically check, kind of, making sure that we have control over our data.
No, that's a great answer. And yeah, I think, it's great to see that you're, already kind of looking into how to mitigate these issues.
Well,
no, go ahead.
People are never going to accept these things. I don't want a world where I'm surrounded by thousands of cameras that I have no idea what, who's looking through them. That sounds like a nightmare to me. So
yeah, no. I definitely appreciate that. And we'll probably post that into, the descriptions that, others can also take a look at that, that you sent us. So yeah, we're almost at time. So I really want to thank you, Pete, for coming on and talking us through this area. I think you gave us a pretty broad kind of overview. I'm sure a lot of people who are tuning in are pretty excited, and us included, and hope to see kind of more work coming from you in the future. I want to thank everybody in the audience for tuning in. Come in, next week. Please go to our website, mlsys.stanford.edu, to see the list of speakers, past and present and future. Subscribe to our mailing list and subscribe to the channel. We're almost at 5,000 subs, so really close. So get us there. And next week we'll have, I think Willem is going to be coming from Tecton to talk about feature stores. So thanks, everyone.